Hey everybody, welcome back to another edition of zkStudyClub. Today we're very excited to be discussing a new paper with some folks who presented here before. Benedict Boons and Pratush Mishra have both presented on this on this channel before, and their grad students have recently also been or worked with them on co-authoring this most recent work, one of whom, Will Wang of NYU, is going to be presenting here today. So with that, Will, please take it away.
Great. Yeah. So thanks for having me. So today I want to talk about some recent work that we've been doing on accumulation or folding. And yeah, this is joint with Benedict, Pratush, and Wilson. Okay. So as motivation, let's consider the task of proving a sequential computation. Okay. So we have some initial state x0, and we want to apply like f, like a function f, a bunch of times to x0. And so one example of this is, let's say, repeatedly hashing some data. And so, for example, like a VDF, you could construct a VDF just by, doing a bunch of hashing, and maybe you want to prove that you did all of this work correctly. Okay. And more generally, we can also consider functions which receive like an additional non-deterministic input. So for example, if you want to prove a VM computation, like in this case, like F would represent the CPU circuit, X would be the current state of the VM, and W would be the current instruction. And maybe you want to prove that, X4 is the result of running 4 instructions on this VM from some default initial state X0. Okay. So formally, this is the kind of statement that we want to prove. Okay. And so if you want to have succinct proofs, kind of the natural approach would be to use a Snark. And, this works, but there are some drawbacks. So the first is that it's not memory efficient. And what I mean by this is, if you actually consider doing the computation itself, you only have to ever keep track of your current state along with like the current input to the computation. But when you're actually trying to prove this in a Snark, it might very well be the case that you need to remember or have all of the states along, like all of the intermediate values along this computation in your head. And so, if T is, let's say, 1,000,000, you need like 1,000,000 different states simultaneously in your memory. And, ideally, there'd be some way to exploit the structure of this computation so that you can also have memory efficient proving. So another issue is that also, for real world evolving computations, the prover often wants to kind of output a proof attesting to the current state of the computation. And then later on, maybe it wants to run some more steps and then publish a new proof for the new current state of the computation. And if you're to kind of just use a Snark in a black box fashion, right, you would have to redo the work of proving everything up to that point, when kind of the only thing that you should be proving is the most recent step of your computation. Cool. So one way to avoid these drawbacks is to use this technique called incrementally verifiable computation. And the idea is as follows. You have some initial state x0 and some empty proof, which is denoted bot. And you have some proving algorithm, which takes the current state and outputs the next state. And additionally, we'll also output a proof attesting to this state's validity. Okay. And the point is you can kind of do this repeatedly. So given the next state and a proof for that state, you can generate the next state as well and a proof for that as well. And you can kind of do this repeatedly for an unbounded number of steps. And at any point in the computation, someone can verify the current state of the computation just by verifying the current proof. Okay. So there are 3 key properties for IVC. The first is completeness, which basically says that given a valid proof for a current state, the proving algorithm is always able to generate a new valid proof for the next state. Okay. Knowledge soundness basically states like given current proof for the current state, there's some way to kind of extract the full history of the computation such that like everything is consistent. Okay, and the final key property of IVC is efficiency, which basically says that the size of your proof, as well as the prover and verifier runtimes, should essentially be independent of T. And this is kind of the key feature which eliminates the drawbacks that I described earlier when it comes to using snarks directly. Okay, so the state of as of like the state of the art, there are kind of two main approaches to constructing IVC. So the first is like a snark-based IVC, and in particular, we'll focus on like a hash-based proof systems. Um, and so yeah, so one advantage of this approach is that you use hash-based cryptography. And this is very useful for a number of reasons. Like computing hashes is very fast on our computers. You kind of have free choice over how to arithmetize your computation. And it's also plausibly post-quantum. Okay. And probably the big downside of using like these kinds of snark-based IVCs is that concretely you get a very high recursive overhead. And we'll get to what recursive overhead means later, but roughly you can think of it as kind of the amount of extra things that you need to prove besides the IVC computation, like F itself. Okay. And so I have this figure that's reported by Fractal, which is essentially recursive Fry, that says that the recursive overhead for their scheme is around 1 million gates. Okay, so the other big approach to doing IVC is from accumulation, which is also called folding. And really the big advantage is that it's incredibly simple. So accumulation avoids a lot of this snark machinery. In fact, as we'll see, it's like these proof systems are almost ridiculously simple. Essentially, all the prover will need to do is make a single commitment to a witness, and then maybe some like basic arithmetic on top of that. Okay. Accumulation schemes also have extremely low recursive overhead. So I have this figure around like 10,000 gates from Nova, which is a very widely used folding scheme. Okay, and so these are great. But kind of the big downside of accumulation is that all current accumulation schemes, obviously with the exception of this work and some concurrent work like latticefold, work with group-based cryptography. Okay, and like group operations are relatively slow, and they also restrict how you arithmetize your computation, and in particular, you're forced to use like these large prime fields, and there's really no flexibility there. As a result, your arithmetic is somewhat expensive. Okay, and finally, it's also not post-quantum. So kind of the big overarching research question that we tackle in this paper is like, can we get the best of both worlds? And in particular, can we build accumulation using hash-based techniques? And the point is, we want to get the benefits from accumulation, like a simple construction, low recursive overhead, as well as the benefits from hash-based crypto. So like very good performance and kind of free choice over arithmetization. Okay, and obviously post-quantum security as well. Cool. So before we actually get into I guess our work, I do want to give some background on accumulation schemes, just because I imagine some of you in the audience might not be as familiar with it. So kind of the goal of an accumulation scheme is to verify a sequence of proofs, right? We have proofs pi1 through pi n, and we want to check all of them. And of course, you can always just individually verify each proof, but the hope is that somehow you can batch the verification together such that you do less work. Okay. And so the key idea for accumulation is that somehow maybe we can fold these proofs into a running accumulator. Okay. And only check the final accumulator at the end. So in this example here, I have like I have a starting default accumulator denoted bot and a proof pi1. Okay, and this folding is going to be implemented by an accumulation prover denoted P, which takes these two things in and outputs a new accumulator ACK1. Okay, and you can kind of repeat this process over and over again. You can run the accumulation prover on ACK1 and another proof pi2 to produce a new accumulator ACK2. Okay, so you do this for all of the proofs. And then finally, at the end, you run this decider algorithm denoted D to validate the accumulator. Okay, and if the decider accepts, like ideally, this should guarantee that the entire sequence of proofs is valid. And this is not quite true. You do need to also verify that each folding step done by the prover was correct. Okay. And this is done by this accumulation verifier denoted V. And just to emphasize, this accumulation verifier is not testing the validity of a proof or an accumulator. It's only testing that the folding was done correctly. And the idea is that maybe checking validity is expensive, but checking the folding itself can be quite cheap. And so if kind of the cost of checking n foldings plus the cost of a final validation is cheaper than the cost of just verifying each proof individually, then the accumulation scheme gives you savings. Cool. So there are three key properties of an accumulation scheme. The first is completeness. So given any valid accumulator and a valid proof pi, the accumulation prover will always be able to output a new accumulator, which is both valid and the folding is also correct. Okay, and soundness roughly says if you have accumulator and a proof, which correctly fold into a new accumulator that is valid, then you know that the old accumulator and the proof are both valid as well. Okay, and you can kind of repeat this process recursively. So if the decider accepted Act 2 in this diagram, and you know that the folding was done correctly, then you know that Act 1 was a valid accumulator and that pi 2 is valid. And then you apply the same argument again to Act 1. If Act 1 correctly folded pi 1, then you know that pi 1 is also valid. And so by this argument, you can kind of recursively show that every single proof was valid. Okay. And the final key property of an accumulation scheme is efficiency, which basically says the size of the accumulator is independent of the number of things that you're accumulating. And also the accumulation verifier V should be very cheap, and in particular sublinear. So this sublinear requirement will turn out to be crucial for constructing IVC from accumulation schemes. Finally, note that in these accumulation schemes, the proofs and accumulators do not actually have to be succinct, right? So they don't have to be Snark proofs. They can just be normal NARK proofs, let's say. And in this case, like the verifier will only access a small part of the proof and accumulator in order to make its decision. And this is very important because the fact that we don't need snarks is why accumulation can be so simple, right? These proofs and accumulators will actually be extremely easy to generate, in large part because their size is linear in the size of the statement. Cool. So how do we actually construct IVC from accumulation? So before we talk about that, I do want to go over constructing IVC from snarks, which is a
Wait,
very
can I ask a quick question?
Yeah, go ahead.
Can you go back to the end of the slide, of the previous slide?
Yeah.
So am I right in understanding that the proof might be like the complexity of the proof might be not succinct, but because it depends on a small part of the data, that's how you manage the sizes of the verification.
Yeah, exactly.
Is that kind of what you're saying?
Yeah,
Okay. All right, thanks.
cool. Yeah, and so this is known as split accumulation. I didn't really go into detail here, but if you're interested, like BCLMS21 is the paper that introduced this idea. Okay, cool. So snark-based IVC. So let's consider a snark with a prover P and verifier V. Okay. And we're going to look at how to actually construct the IVC prover. So first, of course, it's going to evaluate the IVC function f on the current state to produce the next state. Okay, and it's going to prove that it computed this step correctly, just with the Snark prover. Okay, and so the dotted line here just represents the circuit that the Snark prover is proving. Okay, and in addition to that, it also will prove that the old proof outputted by the previous step of the IVC computation was indeed valid. Okay, and by this logic, you can kind of like chain these proofs together such that your final proof is implicitly verifying all of the previous proofs. Cool. And so just to reiterate, the circuit that you're proving not only consists of F, but also the Snark verifier V represented as a circuit. And we say that this additional circuitry is the recursive overhead. So for Snark-based IVC, the recursive overhead would just be the Snark verifier itself. Cool. So this is the construction of Snark-based IVC. So accumulation-based IVC is a little bit more complicated. We start off with a NARC PV. And just to reiterate, this doesn't have to be succinct. Okay, we do the same thing as before. You compute one step of the function and you prove that this step was computed correctly. And in addition, you're going to fold in the previous steps, proof and accumulator, into a new accumulator, Acci plus 1. Okay, and finally, you also need to prove that you did the folding correct. And so for accumulation-based IVC, the circuit that you're proving consists of the step function f, as well as the accumulation verifier v. Okay, and in order to verify the IVC computation, what you would do is you would just verify the proof, and you would also validate the accumulator using the decider algorithm. Okay, and so if you didn't completely follow the construction, it's not a big deal. Kind of the key distinction between the approaches that I want to highlight is, first of all, the NARC prover and accumulation prover will ideally be much faster than the Snark prover. And hence, an accumulation-based IVC prover should hopefully be a lot faster than the Snark-based IVC prover. And second, our recursive overhead is slightly different. So for Snark-based IVC, the recursive overhead was the Snark verifier. But for accumulation-based IVC, it's actually the accumulation verifier. And ideally, we can make the accumulation verifier much smaller than the Snark verifier. And this is what allows us to kind of minimize the recursive overhead of the computation. And these two facts together are kind of what really makes accumulation-based IVC so powerful. Cool. So if accumulation explained, we can finally talk about our contributions. So first, we show how to do accumulation from symmetric key primitives, and in particular, just hashing. And this is with the caveat that our accumulation scheme only supports folding a bounded number of times. Okay, and this property is not captured by existing definitions. It's a bit weaker. And so because of this, we also need to introduce a new definition, which we call bounded depth accumulation, which captures our construction. So again, bounded depth accumulation is weaker than normal accumulation. But nonetheless, we'll show that it's actually still sufficient for constructing IVC. And from a theoretical point of view, the IVC that we attain has a lower asymptotic overhead compared to the prior state of the art. So in particular, fractal, which you can just think of as recursive Fry, has this recursive overhead O of lambda times log squared n. And we eliminate a factor of log n and replace it with this d, which you can think of as like a small constant. Okay. And finally, we also give some optimizations that we believe should significantly improve the concrete performance of our scheme. And so I'll briefly mention the optimizations at the end of the talk as well. All right, so let's actually get into how to construct our accumulation scheme. So our starting point will be an existing accumulation scheme. This can be Nova, Protostar, or kind of like anything else that's been proposed before. But for the purposes of this talk, let's stick with the concrete example, which will be like a slight variant of Nova. So we'll consider this augmented R1CS relation, where the instance is like some matrices A, B, C, D, and the witness is a vector Z. And we'll say it's valid if az.bz is equal to cz.dz, where this dot is the Hadamard product. Okay, and of course in R1CS there's also like a small portion of Z which should be part of the instance, but for simplicity, let's just ignore this. Okay. Additionally, we'll also make use of a Pedersen commitment, which essentially just maps a vector Z to a group element in a cryptographically hard group. And kind of the key feature of a Pedersen commitment, which we'll use in accumulation, is that it's homomorphic. Namely, for any two vectors, right, the commitment to their sum is equal to the sum of their commitments. Okay. So let's talk about kind of what proofs we're actually going to accumulate. And what you'll see is this is kind of like a ridiculously simple proof. It's probably like the dumbest thing you can imagine. So what the prover is going to do is, Okay, it's going to commit to the witness value z to get a commitment z bar. Okay, and it's just going to send z and z bar over to the verifier. Okay, and the verifier is going to literally just compute the augmented R1CS relation. It's just going to check it itself. And then it's also going to check that the commitment is indeed opens to that vector. And so this whole commitment thing might seem a bit superfluous, but it will turn out to actually be useful for accumulation. But this is just like the core narc that we're going to be, whose proofs that we're going to accumulate. Okay. So in order to accumulate, we also need to define the accumulator. So first recall that like a proof consists of a vector as well as its commitment, such that it satisfies the R1CS relation. Okay, and an accumulator will look quite similar. It will consist of a vector W and its commitment W bar, plus a new vector E, which we'll refer to as the error, and its commitment E bar, such that AW.BW minus CW.DW is equal to E rather than 0. Okay. And remember, our goal is to somehow fold a proof and an accumulator into a new accumulator. Cool. So what does this accumulation protocol look like? So at the start, the proof and verifier both have the accumulator Accum and the proof pi. Okay, and kind of the natural thing to do to produce a new accumulator is to, take a random linear combination. So the new accumulators W will just be like a random linear combination of the old W and Z. Okay. And if you try to compute what like the corresponding error term is, you don't actually have to like look at the same equality. The point is that it's actually just the new error term will be equal to the old error plus alpha times a bunch of cross terms, which we'll call T. And so the prover will just like first compute T as well as commitment and send it to the verifier. The verifier responds with the random challenge. Okay, and the prover will now compute W prime and E prime as well as their commitments. And this constitutes the new accumulator Ac prime. Okay, the prover will send this back. And the verifier will check that the prover computed the new accumulator correctly. And it does so by checking the linear relation. And one key detail is that like it's only going to check this linear relation over the commitments. But since the commitment scheme is binding, this somehow enforces that the linear relation holds over the underlying committed vectors. Okay, and in this way you get like a verifier that only touches the commitments and hence is sublinear. Cool. And so just for completeness, I'll also describe the decider. The decider just checks the equality for the new accumulator. And it'll check that the commitments indeed open up to the desired vectors. Cool. So I've described this as a kind of an interactive protocol, but you can always make this non-interactive by applying Fiat-Shamir. And in this case, like T bar and alpha would constitute the accumulation proof. All right. And so if you didn't follow this entire construction, that's also not a big deal because for the rest of the talk, we're really only going to be focusing on a small part. And namely, it's like this pink box. Okay. And the reason is because this pink box is the only place where we actually need to take advantage of the fact that the commitment scheme is homomorphic, right? So recall, like the accumulation verifier needs to check that the linear relation holds over the underlying committed vectors. And so when it has a homomorphic commitment, it can just check it literally by computing over the commitments. Okay. But the fact that we have these homomorphic commitments is kind of why we need to rely on group-based cryptography. And these are kind of the things that we want to get rid of. And so for our first attempt, so this is what the accumulation scheme looks like for like this modified nova. And for our first attempt, okay, let's just get rid of the Pedersen commitments. And we're just going to replace them with Merkle tree commitments, okay? So all I've done here is I've just changed every place where I use a Pedersen commitment to Merkle tree. And now the commitments will just be the roots of the Merkle tree, okay? And because of this, we can't actually do the homomorphic evaluations anymore over the commitments. And so Well, completeness is the same as before. Like if an honest prover just does everything according to the protocol, then everything is accepted. But for soundness, we really need to test this linear relation, right? Because it might very well be the case that a malicious prover commits to a W prime, which is totally unrelated to the original W and Z vectors, right? You really do need to check that W prime is equal to W plus alpha Z in order for soundness to hold. Okay, so let's focus on specifically just checking this linear relation. Okay. So as before, so we have like 3 commitments, and we want to check that the underlying committed vectors satisfy this linear relation. Namely, like the first one is equal to the second one plus alpha times the third one. Okay. And because we can't really do anything with the commitments itself, we actually need to do a bit more work. So one idea is, okay, let's just sample a bunch of random locations on this vector. Okay, I've just randomly chosen a bunch of indices and call this set Q. It's a query set. Okay, and the verifier will send this to the prover. And the prover will respond with the claimed values at these locations across all of the vectors, along with like opening proofs. So for Merkle trees, this would just be like a Merkle path up to the root of the tree. Okay, and the verifier will check that indeed like these opening proofs are valid. And finally, it will kind of like check this linear relation element-wise. So for each index I that we've queried, it'll check that the ith element of W prime is equal to the ith element of W plus alpha times the ith element of Z. And the hope is somehow by like, since we are randomly sampling the locations, like intuitively, that means that most of the locations should be consistent. Otherwise, we would have just randomly stumbled upon one of the inconsistencies. Okay. So formally, we can just consider like, suppose like a delta fraction of the locations across these vectors are inconsistent with each other. Then if you make T queries, then they will all like pass with probably like 1 minus delta to the T. So basically each of the queries needs to avoid, like in order for a malicious prover to succeed, each of the queries would need to not hit the inconsistent locations. Okay, and if this is like some inequality, but like if you set T to be equal to the security parameter divided by delta, then you can show that this probability is negligible. Okay. And in particular, if you want to guarantee that at most a constant fraction of locations are inconsistent, then T will essentially be like O of lambda, and you're happy because your accumulation verifier is only sampling very few points. So there's a problem though, which is like, how do you detect a single inconsistency? So you can imagine like maybe there exists some invalid proof, which only differs from a valid proof at a single location. And from the verifier's point of view, the only way they can distinguish these two cases is if it actually queries this location where they're inconsistent. But if only like 1 out of n of the locations are inconsistent, then you effectively would need to query every single location in the vectors in order to check this. And that kind of defeats the purpose of accumulation, right? We want the accumulation verifier to be extremely small, and therefore it should only be able to query a small number of locations. And so it seems like we're stuck, right? Because we don't want to make too many queries, but if we don't make enough queries, then the prover can always sneak in a few inconsistencies that could like totally ruin the proof. Okay. So to get around this, we're going to introduce a new tool. We're going to use error correcting codes. And just in case anyone is unfamiliar with them, I'll just like give a brief overview of what error correcting codes are.
Sorry, Will, can you go back? I actually had a quick question on the last slide.
Sure.
So I guess like the problem you highlighted actually is worse based on the number of rounds, right? So like if you're doing this round by round, like the more rounds you have, the potentially more
Yeah.
dangerous this problem is. Is that the way to think of it?
Yeah, so for the purposes of like this current example, like it's already totally broken with 1 round, but you're right, like round by round, kind of you would be able to inject even more inconsistencies into the proof. Yeah, you're totally right. And this fact will actually become relevant for our final construction. But yeah, I'll get to that in a sec as well.
Thank you.
Cool. Okay, so error correcting codes. So an error correcting code is just like simply it's just a mapping from n element vectors, which we call messages, to L element vectors, which we call code words. And generally, like, code words will be much longer than the messages. Okay, and the key property of a code that we want to make use of is the distance. And the distance of a code just refers to kind of the minimum Hamming distance between any two code words, where Hamming distance just refers to the number of entries where like two vectors are not equal. Okay. And error correcting codes should also support efficient decoding. Namely, given a noisy code word, can you recover the original message? So let's say we have like a message. Okay, and we encode it in the code to produce a code word. And I'm going to corrupt some of the locations in this code word. So here I've just corrupted at 2 locations, and I've just replaced the entries with like some arbitrary field element. Is there a way to go from this noisy code word back to the original message that we started out with? And an error correcting code is useful if you can do this, in particular for like a large number of errors. So we say that the unique decoding radius is equal to the kind of maximum number of errors allowed. Cool. And finally, we'll also be interested in linear codes. So linear codes are essentially just linear maps. And so you can just imagine C being implemented by some sort of matrix vector multiplication. Okay. And so many examples of error correcting codes are already linear. So this is not really a big requirement. And we'll be interested in linear codes with large distance, like a large constant fraction distance. And for example, like a Reed-Solomon code will satisfy this property, like just essentially optimally. Yeah, and so when I talk about codes, you can kind of just imagine a Reed-Solomon code that maps a message like of a length n to a code word of length 2n, let's say. Cool. So again, this was our first attempt at doing like hash-based accumulation, where we just replaced the Pedersen commitments with Merkle tree commitments. And as recall, like this didn't work. So what we'll do instead is, instead of committing to the vectors directly, we're going to encode to like we're going to commit to encodings of vectors. Okay. So I've highlighted them in blue, but just everywhere where we like committed to it, just like a normal vector before, we'll first compute the code word for that vector, and then we'll do the Merkle tree commitment over the code word. Okay. And everything else is the same as before. Okay. And now to kind of handle this linearity check that's like crossed out in red right now, we're going to engage in the spot check protocol I described earlier. So first, the verifier is just going to sample a bunch of random locations. Okay, and the prover will respond with openings. And the verifier will just check the opening proofs and also check that the linear relation holds element-wise over all of the locations that it queried. Okay. And so completeness actually follows from the fact that the code is linear. Like, namely, we're testing the linear relation over the code words that are being committed to. But actually, like if the original vectors were satisfied the linear relation, then so must the code words, because C is linear. It will just distribute over the addition and scalar multiplication. So we're good with completeness. And soundness kind of crucially relies on the fact that we can do this spot check and not have the prover cheat somehow. And so I'll give kind of like a very brief informal soundness analysis, but it should hopefully just convey the intuition for why this works. So let's say you have like 3 committed vectors and you want to test the linear relation between them. And we'll just call the underlying vectors A, B, and C. And it's important to note that kind of A, B, and C do not have to be code words, right? For an honest prover, they'll always commit to code words, but you could imagine a malicious prover that, you know, just commits arbitrarily to whatever vector it wants. And so really these are just vectors. Now the decider guarantees that the final code word A, like the random linear combination, is actually a code word. So we do know that A is a code word. And the verifier guarantees by the spot check, assuming that you set the parameters correctly, that the Hamming distance between A and the purported linear combination B plus alpha C is at most delta far from each other, where delta is like some constant fraction, like let's say 1/4. And this immediately implies, of course, that since A is a code word, that this purported linear combination is also delta close to the code. Okay. And kind of intuitively, since alpha is just a randomly chosen field element, you want to say that, well, if B plus alpha C is delta close, then like with high probability, then B and C must also be delta close to C. Because otherwise, if one of them were far away, then if you just took a random linear combination, presumably the result would also be far away from the code. And you can like formally prove this using these so-called proximity gaps for code. There are a ton of them out there. But like, for example, for Reed-Solomon codes, we have a lot of very useful proximity gaps. And so if we just take this at face value, B and C are delta close to C, then we can actually conclude that the decodings of A and the decodings of B and the decoding of C satisfy the linear relation that we want. Okay. And the point is, like, if A is a perfect code word and B and C are only slightly noisy, if they obey the linear relation over the vectors, then once you decode them, it should also just obey the linear relation over the decodings. And I mean, in our paper, we give like a better proof using like a more precise proximity gap statement. But just as like a simple example for like confirming this intuition, you can imagine if you encode both sides. If you encode the left-hand side, you just get back A, which is a code word. And if you encode the right-hand side, you get like a code word, which is like 2 delta away from B plus alpha C, like by a triangle inequality. And so since you know that A and B plus alpha C are also delta close, again, by a triangle inequality, you can conclude that like the right-hand side encoded and the left-hand side encoded are 3 delta close to each other. And if like assuming that 3 delta is less than the distance of the code, this implies that these two code words are actually just equal, and hence the decodings are equal. Okay, but yeah, this is just an intuition. And the key thing I want to focus on is, by doing this error correction, we are able to recover the homomorphism check over the decodings, right? Like decode A is equal to decode B plus alpha times decode C. This is like the key fact that we want to use in order to like show that the accumulation scheme is sound. But there is one issue, which is namely that even though A is a code word, our guarantee is not that B and C are code words. They're only delta close to the code, right? So they're slightly noisy. And in general, you can imagine that like, for the first step of accumulation, if you have a valid code word, then what you guarantee for the previous step of accumulation is something that's slightly noisier. And it turns out you can like run the same analysis again on the step before that. But then your only guarantee is that like those code words were 2 delta close, and so on and so forth, like 3 delta, 4 delta. And in general, like if you want to accumulate k steps, then kind of the oldest proof or oldest accumulator will be noisy, like with like k delta noise. And as soon as this like noise exceeds like the unique decoding radius of the code, it's kind of meaningless because you can't make any claim about the underlying decoding satisfying the linear relation. And so kind of just to like wrap it up, in order to support D accumulations, first of all, you're going to set your spot check parameter delta to be some constant such that D times delta is less than the unique decoding radius. Okay. And the point is like this accumulation scheme would therefore be able to support D steps. I do want to note that this also like corresponds to like a real world attack. Like if you set your parameters such that your accumulation scheme only supports, let's say 20 steps of accumulation, and you try to do actually 21 steps, it turns out there's actually like a malicious prover that can break your scheme and like fold in invalid proof. And roughly speaking, the way they would do it, as Alex mentioned before, is they would just try to inject to the inconsistencies just a couple locations per accumulation step. But the point is like after like 21 accumulation steps, then kind of the entire code word has been, or the entire vector has been rewritten to be like some unrelated valid code word. Cool. And so this notion of accumulation where you can only support a bounded number of steps is not, again, it's not captured by the definition that I described earlier. So it does need a new definition. And we give this in the paper. We call it bounded depth accumulation. And informally, it basically says, okay, so this is the original accumulation scheme definition. So if an old accumulator correctly folds into a new accumulator, and this new accumulator is valid, then you know that the old accumulator is valid. And what we're going to say is something slightly weaker. If the old accumulator folds into a new accumulator and the new accumulator is valid, then the old accumulator is still valid, but it's like slightly noisy. And formally, we say that it's just accepted by a weaker decider, like a less stringent decider, which we denote D1. And we can do this just in general for like some decay. If things correctly fold into something accepted by DK, then the only guarantee that you can make for the old accumulator is that it was accepted by even weaker decider DK plus 1. And you say that, okay, well, this implication only holds while K is less than D. And so this is kind of like the flavor of definition that we give for bounded depth accumulation. Cool. Okay. So for the rest of this talk, I want to focus on, I guess, how to build IVC from bounded depth accumulation. So this diagram here is just what like a IVC from normal accumulation would look like. And for us, kind of everything remains the same syntactically. Like you can just plug in our accumulation scheme into this construction. But the key issue is that if you have bounded depth accumulation, then your resulting IVC scheme is also bounded length in the sense that you're only able to prove a bounded number of steps. So if you set your parameters so that your accumulation scheme only supports 20 steps of accumulation, then your IVC only supports 20 steps of computation. Okay, and this is like quite useless, right? Because in practice, you know, maybe we want our IVC to do like 1,000,000 steps of computation, and it would be kind of unrealistic to set our parameters such that, you know, your accumulation supports 1,000,000 steps. And again, if you exceed this length bound, it corresponds to a practical attack, the one I described before. So the key problem that we still have to address is how do we construct like a useful IVC scheme, which supports like a lot of steps from bounded depth accumulation? And the way we do this is actually largely taken from prior work. And so they talk about this within the context of like a theoretical consideration, but for us, it actually turns out to be useful for actually practically constructing IVC. And so the idea is as follows. So for normal IVC, you can imagine like a proof, like you have a bunch of provers and they're kind of aggregating proofs in a line, right? And so if you have t steps of the computation, you need to aggregate like t times. And so the idea is quite simple. We're just going to do like a quote unquote tree-based IVC approach where we, instead of aggregating along a line, we're just going to aggregate along a tree. Okay. And the depth of this tree is going to be log t. And the point is, you know, if you only do log t aggregations, well, like, you know, let's say you set your depth to be 128, then you can support like 2 to the 128 you know, steps of your computation, which is like more than enough. And the point is you only need to do 128 accumulation steps because you only ever aggregate proofs like log t times. This does require generalizing our accumulation scheme to kind of accumulate multiple accumulators and multiple proofs at once, but this can be done, and we show it in the paper. And this technique also just generalizes to higher arities. So in this picture, I've depicted kind of a binary tree, but you can imagine a tree where every node has like 3 children or 5 children, or in general, just m children. And if you have arity m and depth d, then this means that you can prove m to the d steps. Okay. So I call this tree-based IVC, but if you actually look at the literature, there's like a more general form of IVC called proof carrying data, or PCD, which kind of is this concept that I'm describing here. Yeah, but I'll just stick to like kind of a high-level overview of what's going on. And so again, the key point is that the depth is small, and therefore we can instantiate our bounded depth accumulation with that depth, while also being able to like prove a bunch of steps. Okay. So I also want to talk about like how you might actually practically construct this IVC scheme. And the issue is that like our accumulation scheme, the cost grows with the depth d. And so ideally, we probably want d in practice to be quite small, like let's say 2 or 3. And so if we actually wanted to implement an IVC scheme, the way that we envision doing this would be to essentially use our tree IVC with our bounded depth accumulation scheme for like a decent number of steps, and then run a kind of a Snark prover on top. So this prover, the Snark-based IVC on top. So this prover is just going to prove that, well, this tree IVC was correct. And then we're going to generate a new tree. And then we're going to have this prover recursively prove that, you know, the old proof was correct and this new tree is valid. Okay, and we kind of continue this process. And in this sense, we again get IVC. We do rely on snarks, but the point is that the snark prover will only run once every m to the d steps. So realistically, like let's say we set m equals 16 and the depth of our accumulation scheme to be 3, then this means that our snark prover only needs to be run every like 16 cubed or like 4,000 steps. And hence, like, you know, the amortized cost is actually, you know, quite low. So this kind of construction is what we imagine our accumulation scheme slotting into.
And sorry, well, just so I make sure I'm following, the choice of arity, right, has to be less than the D, not D as in depth, but like the you know, your in terms of your decider, like the threshold of weakness, right? Right. So your arity has to be greater than that, or I'm sorry, less than the point at which the individual scheme breaks.
No,
Sorry, is that
so
question
the
makes sense?
arity actually we kind of just have free choice over arity. So you can just use actually any like polynomial sized arity. And everything works out. I mean, this is kind of why I guess bounded depth accumulation is so useful. Yeah.
Gotcha. So go back. I'm just saying here's the motivation for my question. Can you go back a few slides? Sorry, I'm just trying to
sure.
think through following this. Keep going back. One more. Yeah, so basically, I guess what I'm asking is the arity related to the depth bound, but it sounds like it's not.
Yeah, they're largely independent. I mean, there's the arity does contribute to soundness error just in like a very negligible sense. But like the picture I've described here, like it's independent of arity. Essentially, because like you're taking a random linear combination of two things, you know, you might as well take a random linear combination of 3 or 5 things, and kind of the guarantees that you have stay the same. That's
okay, got it. Okay, thank you.
It's in fact just the other way around. The higher you make the arity, the lower depth your tree will be, right? It's only the depth of the tree that matters for this attack.
Yeah. Okay, yeah,
so if you go back to the other slide.
Yeah.
Oh, okay. So I was thinking this is the arity, but it's actually the depth. Okay, yeah, right.
Yeah, arity means how many like
leaves, right?
Like one node, how many leaves or per how many children each node has. And it's basically instead of folding 2 things together, we can fold m things together. It makes the folding verification a little bit more expensive, right? The folding verifier is linear in m, but it really helps. Like you could imagine m like 16 or something. It really helps with lowering the depth of the tree.
Got it. Helpful. And Dara, I think, just commented. Hi, Dara, by the way. It's it's so pretty that the theoretical consideration about accumulation depth turned out to be useful for practice. Answered my question. I don't know if I asked your implicit question, but if I did, that's the first time and probably the last time in history that I will have ever asked a Dara question by accident. So
it was the whole conversation that answered the question. But yeah, it was how does the concrete sort of security theorem depend on the depth, the parameters of the tree.
Cool. Yeah. Yeah. So again, just to note, like this kind of tree-based construction is like in the past is largely theoretical, but if you were to actually implement this scheme, you would want it. And so, I mean, actually, this is relevant to optimizations. Basically, there's kind of a lot of ways that we can try to optimize the tree-based IVC construction in order to get like significant concrete improvements. Okay, so I think we're running out of time, so I'll just like briefly go over these optimizations.
Oh yeah, and we'll just to flag. So we have technically to the half hour. I don't know if you can go beyond the hour, but yeah, we technically have 30 minutes left of the session. If you can go, we can continue. So don't feel rushed if you don't have a control.
Okay, I see. Yeah, so recall that, you know, when we're doing the spot checks, we want to query, you know, each vector at a bunch of locations, but actually like these locations are all the same across the vectors, right? Because we want to test the relation element wise. And so one idea is like, okay, you if I have 3 commitments and I'm doing 3 queries to each commitment, then this requires like 9 Merkle tree paths. But maybe there's a way to do better than that. And the idea is actually pretty simple. If we can somehow prepare W and Z in advance simultaneously, then we can just like commit to both of them at once and just like make the leaves of the Merkle trees like a tuple of elements. Okay, and the point is, well, if you want to query at this location, we just need to open the path once and you've recovered like both of the items. And so in this way, you can kind of reduce the number of Merkle tree openings that the accumulation verifier has to check. Okay. Yeah, again, so if you want to commit to m vectors simultaneously, instead of having like a multiplicative growth and cost, it's actually just additive. Okay. So the second optimization is a little bit more involved. So I'll just try to briefly explain the intuition. But recall that we're trying to like construct this so-called IVC tree for the IVC step function f. And the idea is basically, well, the leaf nodes of the IVC tree are going to actually prove f, and the kind of the internal nodes of the IVC tree are just going to aggregate the proofs together. And in this sense, it somehow like wastes proof space because you're not actually proving anything about f in the internal nodes. And kind of since like your proving needs to be uniform, it's just essentially like proving garbage for no reason. And so the idea is, okay, let's actually just accumulate the proofs for f separately. And we'll use our IVC tree not to verify f, but to actually just verify the accumulation verifier. Okay. Like that's a very rough intuition, but this is kind of the idea of like what we want to do. And the point is that you can kind of get significant savings, like a factor of m, essentially because this technique eliminates the wasted proving of f. Cool. And of course, like you can just see the paper for the details for all of the optimizations as well. Yeah. Okay. So just to conclude, so I guess the main takeaways that I want to give are first, like we construct bounded depth accumulation for NP using basically just hash-based crypto. And we do this at a high level by kind of emulating the homomorphism using error correcting codes and spot checks. And from a theory point of view, we show that bounded depth accumulation suffices for constructing bounded depth PCD, which is like this the tree construction. And this in turn implies polylength IVC by some prior work. Okay. And we find like asymptotically our IVC scheme also has, or our PCD scheme has a smaller asymptotic recursive overhead compared to the state of the art in terms of hash-based PCD. Cool. And for practical constructions, we give some optimizations, and kind of it's an open problem. Like we're working on this right now, just in terms of implementation and stuff, like how to actually set the parameters such that we get the best performance possible. But we're pretty optimistic that these techniques will translate to real efficiency gains for doing IVC.
And just when you say parameters, you mean like this is like the arity and the depth?
Yeah, exactly. Like the arity, the depth, like at what point do you want to start doing the Snark proving on top? Yeah, that sort of stuff. Cool. Yeah, that's it. Thanks. And you can find the paper on ePrint at this link.
Okay, awesome. Thank you very much, Will. This is a great presentation. I guess we can open it up for questions. Does anyone have questions for Will?
Not so much of a question, but an observation. So so you're using Merkle trees in a context where you have a bound on how many times you can do something. That reminded me of Sphinx, where you're which is the post-quantum signature scheme that I was involved with, and there you construct the overall signature scheme in terms of few time signature schemes, which are insecure if you use them too many times. So I need to kind of check. You may have already done all of the optimizations from that context, but yeah.
I mean, I don't know.
I'm
not so familiar with Sphinx. I mean, it sounds intriguing. Yeah, I mean, it's definitely the case that, you know, maybe there are more optimizations to do here. I don't, yeah, I wouldn't really.
Yeah, I mean, so Sphinx was basically sort of designed by throwing as many orthogonal optimizations together as possible. Yeah.
Cool.
Any other questions for Will?
Yeah, just a quick one. So just to make sure I understand, so the recursive overhead that you would end up getting for the scheme is verifying a few Merkle path, which is proportional to the distance parameter that you set, plus one Fiat Mirage, roughly, plus a few like linear field operations, correct?
Yeah, exactly. That would be the recursive overhead.
Oh. And the hash that you will be using for the Merkle trees, I assume that you would also need to use, you would try to use something like Poseidon to also further reduce the recursive cost of that, I guess, right?
Yeah, I mean, it would definitely help, right? Because, yeah, again, like the accumulation verifier, like the only thing that accumulation verifier actually needs to do is be represented as a circuit. So, yeah, it would be like using a circuit-friendly hash function would, I think, give you a lot of savings.
Okay,
it's actually an
makes sense.
interesting case where you might want to use something like what are they called? The reinforced concrete ones, like bricks and brick and mortar or something. There's like basically this family of hash functions which are both, or like the newest families of hash functions are both circuit friendly, but they're also fast on CPUs, right? Because the most costly operation, unlike in a group-based Snark, is now actually the hashing. So you care both about the circuit friendliness and about it being fast. But it seems like at least there are proposals for hash functions that get you the best of both worlds. Hopefully they're also secure.
Yeah,
That's always
there's a recent one that is using the tower binary field construction. I haven't checked how it compares to others.
To complete on Giacomo's question, like the requirements for the hash function are to be collision resistant, I guess. But I was curious to know whether if you change from sort of the linear folding to the sort of tree part, if the requirements for the hash function concretely change. There are like other types of attacks that you can have because things are done in parallel rather than sequentially when you fold things together.
Yeah, I don't think anything changes. I guess all of these things are, like we prove our accumulation scheme in the random oracle model. So, okay, it's secure with random oracle. And then, I mean, presumably if you just use like, if it's just Merkle trees and that's all you care about in terms of like your guarantees, then it should be fine once you instantiate it, even if they're, yeah. But, yeah, I mean, I guess the way we prove it is we prove the accumulation scheme is secure in the random oracle model. Then we apply Fiat Shamir to get an accumulation scheme in the standard model, and then we do like a proof that like PCD and IBC bill on that is secure. So I don't know. I think it should be fine.
Thank you.
Okay, maybe if I have another question, I'm not sure Michele still had something.
No, it's all good. Thank you.
Okay, so have you given some thought on like instantiation with like different like maybe not effective friendly fields, small fields, and different codes? Like it seems to me that for you only use the read Solomon mostly for the linearity property, efficient encoding and good distance, and then because you have a strong proximity gap threshold. So it looks to me like the construction could very easily be ported to smaller field, different codes. Of course, then you don't have the strong proximity gaps, but you can do other things.
So we do give like an alternative construction. Okay, so yeah, I guess first of all, for the accumulation construction I described here, you actually could just replace it with I think like even arbitrary linear codes, and there's like a good enough proximity gap. For the general case when we're trying to fold like multiple accumulators and multiple proofs at the same time, the random challenges won't actually be uniformly distributed. In that case, you do care about like specific proximity gaps for specific correlations. And that's why we use Reed Solomon. But in the paper, we do give like an alternative construction that's slightly more expensive. But again, and that one actually just works over for arbitrary linear codes, because essentially it's just going to make uniformly random linear combinations. Yeah, that's like 6.4.
Okay, and you could also use tensors, I guess, and that also gives you there are opportunity gaps for general codes in that sense for tensor challenges, and you can probably use that.
Yeah.
Yeah, I wonder if there's like any like any like significant obstacle to getting like to a BNews like accumulation scheme, but it does
I
not
really
seem
don't
to
think
me
so.
like.
I mean, I think it's mainly just because we're not as familiar with it, but I don't think there's any sort of like fundamental obstacle to getting that.
I mean, this is
Yeah.
kind of the nice thing about these accumulation schemes is they're so that simple. And all we do essentially is replace the homomorphism with this linearity check. And as long as, and yeah, we show that, so the key technical tool there is this proximity gap. And we show this works for arbitrary linear, or we have a construction where we can use a proximity gap result for arbitrary linear codes. So we can work with any arbitrary linear code, linear time encodable ones like the breakdown code, Binnius things over binary fields probably. There really is no limits.
There's a footnote in the paper saying we only claim plausible post-quantum security as we prove our construction in the random oracle model instead of the quantum random oracle model. Is that just we haven't proven this yet?
Yeah, I mean, it's basically just we haven't. No, it can be done. I think it's actually pretty straightforward. So there's some existing. So you can rephrase our accumulation scheme as kind of like this just general interactive oracle proof that's run by round sound. And there are these, like there's this paper by Chiesa, Manohar, and Spooner that kind of show how to just generically prove that these kinds of things are secure in the Q-ROM. And so I think you would just be able to do that.
Okay, thanks.
Cool. Dara, you still have your hand up. I'm assuming that answered your question.
Oh, sorry.
You forgot to turn off your hand.
Yeah, that's
Yeah.
I just didn't know my hand.
Just making sure.
Is that this paper that I'm putting in the chat? Or is that something else? Sorry, what were the authors again?
Which
Actually, no,
the paper I just mentioned.
No, that's probably a different paper.
Yeah, I
maybe
think the one referring to is Chiesa, Manohar, Spooner, 2020, if I remember correctly.
Yeah, I forget the title, but it's like, yeah.
Succinct arguments in the quantum random oracle model.
Yeah, I just pasted it.
Yeah, thanks.
Cool. Anyone else have any questions on this paper, on this talk? Questions for Will or Benedict? Okay. Well, thank you very much, everyone, for being here. Thank you, Will, for presenting. This is a really great talk. Thank you for coming on ZK Study Club today.
Yeah, thanks for having me.